start off by giving you a warning just before we even jump into this. I was going through the material that I wanted to talk to you about this evening earlier today, and traditionally I do that, and I start with a whole bunch of stuff, and I spend about 2 or 3 hours sort of culling things out and throwing them away to make sure that I can actually make the talk fit into the allotted time. The problem was that I just sat there, instead of throwing things out, I kept adding stuff all afternoon. So be forewarned, I am probably going to go long. If that is a problem for your time and you have to leave early, I promise I won't be offended. That said, I will point out that outside the doors there are armed guards, and they have been instructed to take out the first person out the door. So you're on your own. Anyway, in terms of what I would like to talk about this evening is really just sort of go over fairly quickly a little bit about the Mars exploration program that is currently being conducted by the US, by the European Space Agency, and by the Russian Space Agency as primary components, and with also additional participation by several other countries, excuse me, including India, Japan, a developing effort from China, as well as several other nations. And sort of go through what we're all doing, why we're doing it, and then jump in specifically to one example mission, the Mars Science Lab mission, which flew the Curiosity Rover to the surface of Mars, landed in August of 2012, and use that as an example of sort of the way we design robotic systems to explore another planet, and then jump into a little bit of discussion about sort of what's next. I will say, by way of background, I am a computer scientist and roboticist first. My degrees are computer science and my graduate work in artificial intelligence. I am, therefore, interrupt-driven. If you do have questions, it's okay if you want to yell them out if there's something that's really not clear. I really won't mind, but also we are going to have a dedicated Q&A session at the end. If you want to save it until then, it's not a problem at all. So let's sort of jump into the entire set of material and start off by saying, what's different about Mars? What's the same about Mars? What do we know? What do we not know? It's the next planet out from the sun. It's the 4th planet in our solar system. It has been of interest to mankind ever since basically we took the first look up into the heavens and noticed that some of the stars moved relative to the others. The one that was brightest and closest was Mars. It got our attention fairly quickly. One of the things we've learned, or several of the things that we've learned since then, is we've tried to draw comparisons between the Earth we know and this next planet out, was to try to understand the similarities. So here's a couple of just sort of data points to introduce you to the planet. Mars is about half the diameter of Earth. This gravity is approximately 1/3 of Earth, which means if you weighed 120 stone on Earth, you're going to weigh 1/3 of that, or 40 stone, on the planet Mars. One of the best diet programs anywhere. The only problem is the price tag associated with it is a little bit steep. In terms of overall environment, Mars does have an atmosphere, just like Earth does. It has climates, it orbits the sun, and actually has axial tilt that causes it to have climate or seasonal changes throughout the year, just like the Earth does. So on Mars, there is a winter, summer, spring, and fall. The big difference is a Martian year is about 2 years long. It's about twice as long as an Earth year, and so each of the seasons is therefore about twice as long as they would be on Earth. A Martian day is very similar to an Earth day. We actually call a Martian day a sol, S-O-L. Basically, a sol is 24 hours and 40 minutes, so just slightly longer than an Earth day. So if you were able to go and sit on the surface of Mars and try to live there, your internal clock wouldn't get too screwed up, just a little bit. Let's see, other similarities. The Martian temperature regime. If you were sitting on the surface of Mars at the equator in the height of summer at midday, it actually would be very, very comfortable. You could take off your shoes, wiggle your toes in the sand, and they would be nice and toasty, and you would be having, you'd probably see temperatures in the 25 to 35 degrees C range right down at the surface. It actually wouldn't be too bad at all. One of the interesting artifacts, though, is the Martian atmosphere, as I mentioned, does exist, but it's also very, very thin. Therefore, it has a lot of problem holding temperature, energy, thermal energy all by itself. So what that means is it drops off very, very quickly as you gain altitude. Your toes might be nice and toasty and warm and wiggling them in the sand. The only problem is about waist height, you'd be right around 0 degrees C. Head height, you'd be about 10 below. Gives a whole new meaning to the phrase freezing your ass off. The other thing is the Martian atmosphere, as I mentioned, is very, very thin. It's about 1% the density of the atmosphere on Earth. As a result, it's sort of the pressure equivalent to trying to stand on top of a 100,000-foot tall mountain and trying to breathe. You'll be successful, just not for very long. All of that basically creates an environment that in certain strange ways makes it very similar to Earth if you were to actually stand on the surface and actually try to observe the environment. And so as we start to get into this and start to look at some of the pictures from the surface, you'll notice just that they seem in one way just very, very familiar, yet at the same time they are completely alien. And that's a very typical reaction that we get a lot as we start talking about the planet. Okay, so why do we actually want to go to this place? What's the purpose in trying to understand it? We're basically motivated in the Mars exploration program by 4 fundamental strategic questions. And there's a long, drawn-out process that's used to define what these questions are that involves big, huge bureaucratic meetings of hundreds of planetary scientists from all around the world getting together, debating and arguing back and forth and throwing things at each other and whatnot. And they do this about once every 10 years with what's called the decadal survey. I'm not going to bore you with all the details of that, other than to say that every now and then fistfights do break out, and they're loads of fun. But when they go through this process, and what they have developed in terms of driving and motivating the Mars exploration program is a set of 4 fundamental strategic questions that we're trying to investigate and understand about the planet. The first and foremost, and let's go ahead and get this one out of the way right now, is there the possibility that life may have existed on Mars any time in its ancient past? If it did exist, did it persist? If it did persist, did it evolve, and is it still there? Is something we've all wanted to ask, and we all want to try to understand the true answer to that question. I will sort of leap ahead and tell you the end of that story. There may or may not be life on Mars right now as we know it. We don't have hard evidence yet that any of us can actually point to and say it's there. However, what I can tell you is whenever the first human mission to Mars takes place, and we'll talk about that in a little while, at that point, we will contaminate that planet, and there will be life on Mars at that point forever afterwards. So it's just because when humans go to places, they're dirty, they're nasty, and they leak, and it's just, they're going to get stuff messy. Anyway, we're trying to decide, or trying to determine if there's any evidence to indicate whether life may have existed in the ancient past prior to us actually getting there to contaminate the planet. The other thing we're trying to understand is the Martian climate. As I mentioned, it does have an atmosphere. It does have a climatological environment that changes over time. We do know that Mars used to be much warmer. It was much wetter on the surface than it is now. Something happened to turn it into a relatively dry, arid planet that's relatively cold. We don't know the cause of that change yet. We want to try to understand that, primarily to understand if that is something that could ever happen here. So there's a big part of self-preservation in the answer to that question. Geology. Mars is a rocky planet, just like Earth is, just like Venus is. And we want to try to understand how Mars as a planet has evolved during the early part of the solar system formation, again, as a way of better understanding how Earth evolved. And so there's a lot of self-reflection in pursuing that question. And then the final piece of it is understanding what Mars is like in terms of potential future habitat for humans. We will someday send people to Mars. Are there resources there that those people can use to actually sort of live off the land rather than trying to take everything with them? We do know already that there is a fairly large amount of water already bound up in the systems on the surface and subsurface. If that's accessible and can be extracted, that means there's a whole lot of water that we don't have to take with us when we go to Mars. We can just grab the resources that are there once we arrive. And if you get water, all sorts of magical things happen because you can crack it apart, you can get oxygen to breathe, you can turn it into rocket fuel with a hydrogen, all sorts of other stuff just magically takes place once you find the water. So those are the big motivating questions that we have to try, or areas of investigation that we have. How are we actually doing this? A real quick summary of the sort of stuff that's happened over the course of the past couple of years and where we are going next. Over the past, basically since the start of the 2000s, we had the Opportunity and Spirit rovers that landed, in early 2004 as the first surface exploration of the planet. Spirit and Opportunity were 2 rovers. They were about the size of a small golf cart. It's probably the best comparison. They were designed to last for 90 sols, drive a grand total of 600 meters over the course of their lifetime. Spirit lasted for 6 years before she finally got stopped in a sand trap and had to shut down. Opportunity, as of today, is on Sol 4,931 of her 90-sol mission and is still going. That 600-meter traverse capability that we had to prove and demonstrate, we passed that a long time ago. The odometer on Opportunity right now is past 42 kilometers. If only they would make cars that well. The Phoenix mission landed in 2007, basically a still lander that came down one place, did not move after it landed, but basically landed near the North Pole of Mars and did investigations in the North Polar region, including the identification of water ice near the poles. We knew that the planet had polar caps. We actually can see them contract and expand with the seasons every year. But we thought it was all just frozen CO2, dry ice. Turned out it's actually a lot of water ice as well, further giving us information about the amount of water that's reserved in the entire Martian system. We have a whole bunch of orbiters that are there that are in place there by the US, by the European Space Agency, and by the Indian Space Agency, Odyssey, Mars Reconnaissance Orbiter, Mars Express, and the Mars Orbiter system from India that are all still there operating, collecting data. They also act as communications relays. We're basically doing double duty with all these orbiters by making them into a communications network around another planet. So just like we have communications satellites here on Earth, we're doing that on an interplanetary basis right now as well. Additional orbiters that we launched in 2013 and 2016, MAVEN, which was mentioned earlier, which is looking at the upper atmosphere dynamics that are going on around the planet. The European Space Agency Trace Gas Orbiter, again, looking at atmospheric science. But of interest to me, because I'm like a robot guy, is the set of stuff that's going on down at the surface. I mentioned the two rovers and landers that got there earlier in this decade. Most recently, we had the Curiosity Mars Science Laboratory rover that landed in August of 2012. This is a fairly large rover. It's about the size of a Cooper Mini, weighs in just about 1 ton, is a fairly substantial science platform, and is the precursor for a number of rovers that we're going to fly out near the end of this decade. So let's talk a little bit about what this rover is. Okay, I promise you, this is the only word chart that I will make you be subjected to. To justify my trip over here, I had to guarantee I was going to teach something. This is it. Once we get past this point, it's all fun. So the primary science goal of the Curiosity rover when we decided to fly it was to explore at least one landing site as a potential habitat for life, assess its potential for preservation of biosignatures. In other words, we knew that Mars at some point in its past had a lot of water. We knew it was a warmer place. If there's warmth, if there's water, if there's chemistry, i.e. the minerals that are already there, those are all the key ingredients, as best we understand them, for an environment that's capable of supporting life. And notice I worded that very, very carefully. That's not saying that life exists on Mars. It is saying that at one point, there was an environment on Mars that if life could have existed, the environment would allow it to persist and be supported. And we wanted to find that and prove that it existed. That was the purpose, the primary purpose behind this rover. So the objectives were to assess the biological potential of the landing site, characterize the geology and geochemistry, investigate the role of water in the environment, especially if it's still there, and also characterize the spectrum of surface radiation in the context of understanding what the radiation environment is and what would the likely effects be on human beings when they go there. Okay, so notice the mapping of those 4 things to the 4 big strategic objectives. Again, this is sort of what motivates us to do this sort of stuff. Okay, I promise that's the last thing you had to learn from tonight. Okay, so let's talk about what this rover is that we actually built. Here's a quick overview. There's a rover that weighs about 1 ton, about the size of a Mini Cooper, that we're going to put down on the surface of another planet and operate remotely from about 220 million kilometers away. That in and of itself is really, really pretty cool, but we found out from the American public that if we were going to ask them for $2.5 billion to do this thing, other than just driving around, they actually wanted us to do something. And so they said, well, go and actually have some like science return associated with it. So we basically selected a whole bunch of science instruments to stick on board the rover. And they included all these various different devices. The ones that are sort of right over the top are what we call the remote science package. DAN, which is an instrument that was contributed by the Russians that actually looks at the radiation environment. REMS, which is the weather station that's on board. MassCam, which is the set of high-resolution imagers, cameras that are there. The Molly, which is a very close-up camera that's used on the end of a robotic arm that we can take out and actually put up against the rock and get very detailed microscopic images. The ones across the bottom are the rest of the contact imagers, or contact instruments, including the alpha proton X-ray spectrometer. I'm not a chemist, so that's my one chemical statement for the evening. I used to know what it does, but now I can just say it. There's Marty, which is one of the descent imagers that actually gives us a downward-looking image as we came into land. There's Kemen, which looks at the mineralogy of the rocks and the environment that we're driving across. SAM, the sample analysis at Mars package, which is a very intense wet chemistry lab that's actually inside the box of the rover body itself, where we'll bring samples, ingest them, and basically do a detailed chemical analysis and send the results back to Earth as a remote chemistry lab. And then my very favorite, which I skipped over earlier, ChemCam. Yes, we have a robot on another planet that has a laser on its head. And we can use that laser from up to 100 meters away to blast a rock, vaporize the rock, and with that little puff of vaporization, we actually look at the sparks that are created, and the particular spectra associated with the color of the spark tells us about the material that has just been vaporized by the laser on the head of a robot on another planet. I happen to think that's really cool. Okay, so take the top off the rover and take a look inside, and what are you going to see? SAM, the sample analysis at Mars package, that's that big gold box to the lower left. That's an instrument that was developed by the Goddard Space Flight Center in the US. Kemen, the source of the laser, is immediately above that. The spacecraft computers, there's actually 2 dual-string space computation threads inside the rover that allows it to understand the commands that we're sending and actually execute the stuff that we want it to execute. The motor controller for actually driving the different actuators that are all scattered throughout the entire rover, drive the wheels, the various different the motors associated with the arm, things like that. The X-band radio on the lower right for our communications pathway, power electronics, thermal loop for actually keeping the entire thing warm, things like that. Again, we're in an environment where, as I mentioned, during the summer, at the equator, in the middle of the day, it can be nice and toasty warm. However, during the winter, in the middle of the night, very typically we see temperatures below negative 100 degrees C. So thermal control becomes a big issue for us. You would think that our biggest problem, especially with temperature excursions like that, is keeping the robot warm. No, actually, it is keeping it cold enough. The thing that is basically mounted on the rover just to the right on this image, it's not actually in this image when this picture was taken, but is mounted very late in the process as we assemble it, is what we call an MMRTG, multi-mission radioisotope thermoelectric generator. Basically, it's a nuclear power source that we stick on board that sits there and cooks at about 600 degrees C, wrapped in a whole bunch of thermocouples that convert that thermal energy into electricity to power the rover. We've got a 600 degrees C oven sitting right next to the entire rover. Our problem is getting rid of all that heat, not actually keeping the thing warm. Here's a good image of the rover itself as it's getting prepared for closeout and being sealed up, and that sort of gives you a good idea of the scale and the size of the vehicle itself. There are 6 wheels that are wrapped around it that are used on an independent suspension system. It's a really actually sort of neat suspension system. It's just a bunch of levers and hinges. There's no springs in it or anything like that, but it guarantees that all 6 wheels stay in contact with the surface at all times to give us the utmost traction capability. Once the rover is assembled, we then start to basically build the entire spacecraft out from around it, and it's sort of like putting together one of those old classic wooden Russian dolls. First thing that happens is we take the rover, we fold it up, and then we have the descent stage. The descent stage is effectively a rocket-propelled helicopter that we're going to use to actually lower the rover down to the surface of Mars. So we take the descent stage, and the nozzles that are at the 4 corners, which are those rockets that basically allow us to lower it down, and we stick them at the corners, and we wrap the rover up inside it. So what you see here is basically the rover tucked up inside, and this whole thing that's sort of wrapping around it is the descent stage with the set of rockets off on the 4 corners. So that whole thing is then wrapped up and sealed, and then it's tucked up once it's sort of rover, descent stage, and then around that goes something called the back shell, which is basically a big part of the spacecraft that shields it during the interplanetary flight from Earth to Mars. And so it's all tucked up inside, and you're actually seeing the rover looking from the bottom in this image, and you can see the sort of 6 silvery things that are wrapped up are the wheels of the rover. Finally, that back shell is mated with something called the Aeroshell that sticks on the bottom. And that is basically going to be the thing that's actually going to hit the top of the Martian atmosphere first once we arrive at Mars and convert all the kinetic energy associated with traveling to Mars into heat and slow the spacecraft down. And so it's now all wrapped up, and on top, that sort of cylindrical shape with all of these little square panels. Oops, there we go. All of these little square panels, that's called the cruise stage that actually powers us, provides communications and everything like that on the trip from Earth to Mars. That whole stack is then sent from Southern California, where it's been assembled at the Jet Propulsion Lab, off to the Kennedy Space Center in central Florida, where it's basically mated with the actual launch vehicle, the rocket, for the first time. We buy a really, really big rocket because we're going all the way to Mars. The problem is we have a really, really big rocket and a really, really small payload. This entire structure right here and right here, that's the nose cone of the rocket. This little thing on the floor, that's our entire spacecraft. We have to buy a really, really big rocket because we need that much energy to actually throw our spacecraft all the way from one planet to the next. It turns out the only way you can do that is you buy a really, really big rocket. It automatically comes. There is no option for the size of the nose cone you get. It's basically just one selection on the option sheet. And so you get the nose cone that they give you. And so it happens to be a lot bigger than we actually need. So there's a whole lot of empty space in there. Now, we did entertain a whole lot of different ideas about ways to fill that empty space, most of them centered around use of different politicians to fill the volume. Yeah, we won't follow that path. Anyway, so then all that stuff got stacked together, and then on the 26th of November 2011, we launched from Kennedy Space Center, and we were on our way to Mars. There's a whole separate 2-hour-long talk associated with why we picked that particular date. And it all involves planetary dynamics and where Mars was and Earth is and relative to each other and when we can launch and all this sort of stuff. I will tell you that none of that matters to my mom because she is, to this day, still convinced that we chose to launch on the 26th of November 2011 because that happened to be her 80th birthday, and it was the very best way to celebrate it possible for me to give to her. I've tried to explain, no, I'm not going to do that with taxpayer money, but she doesn't believe me. Anyway, so we launched to Mars in November of 2011. 7 months later, we go through the process of entry, descent, and landing. Okay, so the first thing we had to do somewhere in there is actually pick where on Mars we were going to land. There's a 4-year-long process involving hundreds of scientists and lots of bureaucracy and lots of screaming and yelling that was used to select it. But the end of the process is we selected a place called Gale Crater, which is approximately near the equator on the surface of Mars. It's a 90-kilometer diameter crater that has one really, really interesting feature. Is if you look, here's the entire crater itself, as I say, about 90 kilometers across, but right here in the middle is a 5-kilometer tall mountain, which we thought was really interesting. And basically what we wanted to try to do was land somewhere within a drivable range of that peak and start driving up the slopes of that mountain with our rover. Basically, the belief was, using the knowledge that we had from orbit of this site, that we thought there was a whole lot of stratified layers making up this big, huge 5-kilometer tall mound. And if we could drive up the slopes of the mountain, it would be like driving back in history. And we actually would have laid out before us several million or even billion years worth of past geologic history of the formation of the planet that would be laid open like a science textbook for us to just sit there and read and understand. That was the theory. And we thought, hey, that's a good idea. Let's go to Gale Crater. So we launch. 7 months later, we arrive at Mars. We hit the top of the Martian atmosphere at 12,500 miles an hour, which is just about 20,000 kilometers per hour relative velocity to the planet. I really like using metric a whole lot more than numbers, much more impressive. So we hit the top of the Martian atmosphere at 20,000 kilometers per hour. That heat shield, the last thing that was attached, is the first thing that hits the Martian atmosphere. It, by basically converting that kinetic energy into heat energy and burning away, it slows the spacecraft down from 20,000 down to about 2,000 kilometers per hour. At that point, the largest supersonic parachute ever built gets deployed at an altitude of about 20 kilometers. It slows the spacecraft even further, from about 2,000 kilometers an hour to 160 to 200. At approximately 2.5 to 3 kilometers above the surface, the largest supersonic parachute ever built gets ejected. And then you have that back shell, which was the second to last thing that I mentioned. It gets thrown away, and all of a sudden the rocket-propelled helicopter fires up. The rocket jets start firing, and this thing starts flying its way very slowly down towards the surface, from about 1.5 kilometers up all the way down to a point just a few tens of meters above the surface. And as that's happening, this entire spacecraft is continuing to slow down from 200-ish kilometers per hour down to eventually a relative velocity relative to the surface of Mars of 0, about 10 meters above the surface, if everything works right. At that point, interesting things start to happen. We do something called the sky crane maneuver, where we're hovering on these rocket jets. And all of a sudden, this rover that's tucked up underneath the descent stage gets lowered on a set of 3 ropes, and the wheels on the rover pop open just above the surface, and we actually set the rover down on the surface while it's still connected to this rocket-propelled helicopter that's hovering above it. And once we get down to the surface, the rover senses, I'm actually in contact with another planet, I'm where I belong, I'm home. Cut the bridle free, and the descent stage then flies away and impacts about 1 kilometer downrange, is having done its job. Okay, that's what's supposed to happen during the process. What I'm going to play for you now is, I mentioned one of the instruments that was on board, MARTI, which is the descent imager. It's actually a camera mounted to the bottom of the rover, looking straight down during that entire process. What you're about to see is the rover's MARTI reference point of view of that entire descent and landing process, overlaid with the real audio that we were doing during the actual descent and entry, as we started to figure out what was actually going on during this entire process down and getting down to the surface.
Thrusters have been re-enabled. We will control our attitude on shoot. We are decelerating.
Okay, heat shield just fell away. We're getting our first look from about 8 kilometers up of the surface of Mars as we look down from the rover point of view.
Again with risk mode dynamics.
Risk mode is nominal. We're at 9 kilometers and descending.
Active.
Valid range.
Net filter converged with a velocity correction of 0.7 meters a second.
We've acquired the ground with the radar.
They just got the first indication the spacecraft is actually slowing down, so this rocket-propelled helicopter is starting to work.
Occultation as expected. We're standing by to prime the Emily engines in preparation for powered flight. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending.
Flight EDL, we've got some tweedo warnings. It is in battle short mode, so I should power through them.
Direct to Earth communications at this time. We may have lost it already.
Okay, there are 3 orbiting satellites that are watching this process. They all happen to be right near the horizon, and they're slowly starting to sunset while all this is going on. So they're talking about losing comm with a couple of satellites. That was expected.
We've lost tones from Earth at this time. This is expected. We're continuing on Odyssey telemetry.
Ground solution equals minus 10.8 meters, vertical velocity of minus 82.8
We are priming
meters per second.
start enabled, standing by for back shell separation.
Signal to Odyssey is still strong.
We are in powered flight.
Okay, so they've fallen completely free of the back shell at this point, and they're completely flying solely with this descent stage
About
rockets.
70 meters per second.
Signal to Odyssey
Control
remains
air.
Down to 50 meters per second. 500 meters in altitude. Standing by for sky crane.
Okay, they're down low enough. They're getting ready to drop on the sky crane, basically to lower the rover on the
Nominal.
cables.
Altitude error 5.9 meters.
We found a nice flat place.
Okay, you can
We're
see the dust being
ready for
picked up
sky
by the
crane.
rockets a little bit. It's very faint in these images, but you can see it. And in a second, you'll
Down to
see
10
the
meters per
wheels
second.
pop down and
40
come
meters
into
up.
view. There, you can see the front left wheel actually dropping into the frame of view.
Sky crane has started. Descending at about 0.75 meters per second as expected.
And in a second, you'll hear
Expected
Jody
climate
Davis go
building.
Tango Delta nominal. I'll tell you what that means in a minute.
Signal to Odyssey remains strong.
delta nominal.
Remember that remark.
Yeah. EEVdiscover.
REM stable. REM stable.
Okay, the camera is basically shadowed by the entire rover now down the surface. You can't see much.
Touchdown confirmed. We're safe on Mars.
They get a little bit excited. Okay, so what was happening during the last 60 or 70 seconds there, when Jody called out Tango Delta nominal, basically what she was saying, touchdown nominal. We've actually touched down. The rover has sensed that we're on the surface. But we were really careful because we knew basically the press and the public and everyone else was listening in on a communications loop. So we didn't want to say touchdown nominal and have everyone assume, hey, we're down and we're safe because the process wasn't finished yet. So she basically uses the code word. Everyone in the system knew what was going on, but they also knew there was a couple important things that had to happen before we actually were safe on the surface of Mars. Okay, so you have this rover that's popped open, hung down from the sky crane, flown in, touched down. We actually made touchdown. Jody's called it. And then a couple of things have to happen. Remember, we have a rocket-propelled helicopter sitting 10 meters over our head right now, burning a lot of fuel. This thing is basically a propulsive bomb. We need to do something really important, get rid of it. So the first thing that has to happen once we're down is we have to cut the 3 cables that are connecting us to the rocket-propelled helicopter. So that's one of the succeeding calls that comes in. The second thing is this thing has to propel itself away. That was the second call comes in. The third thing that has to happen is we have to, when the descent stage flies away, it clears the communications pathway from the primary antenna on the rover to link back through the Odyssey orbiter back to Earth and send a signal. We had to wait until that signal came on strong to know that not only had we cut the cables and the descent stage had flown away, but it didn't just go straight up and come straight down. That would have been a very bad day. Instead, it will go up and off to one direction and off to the side where it would impact about 1 kilometer away. So all those things were happening after we touched down before we could say we're safe on the surface of Mars. And then everyone goes crazy. And if you saw the pictures of the time, that's when everyone in the blue shirts, they're all jumping up and down and screaming and hugging and that sort of stuff. And the public affairs officers loved it. Anyway, so here's what actually happened with all that stuff. We have Curiosity that's actually sitting right here in the center of the frame. The back shell and parachute that I mentioned, well, actually, let's start. The heat shield, which was the first thing that we threw away, basically continued on downrange about 2 kilometers and impacted on the surface. The back shell and parachute that were the second parts that we basically got rid of before the sky crane took over. They fell off to the side of the entry path, which was along here, and we're sitting down on the surface. The sky crane itself basically came in, dropped off Curiosity, then flew backwards and impacted about 1 kilometer away. And so all that stuff is still sitting out on the surface of Mars. So that's sort of how we got down to the surface. Okay, once we got there, then what happens? Well, we begin early surface operations. And what does that really mean? Well, the first thing we want to do is we want to take a look around and find out where are we on the surface of Mars. One of the things I didn't mention when I showed you the picture of Gale Crater is we're targeting Gale Crater. We are actually targeting a spot in Gale Crater where we're trying to send this spacecraft. We've got really good with spacecraft navigation over the years. It used to be if we said we want to go to a spot on Mars, all we could guarantee is that we would land somewhere within about 300 kilometers of that spot, and that was about it. Hey, but when you're talking about distances of 330 million kilometers to get to the planet to begin with, being within 300 kilometers at the destination is not that bad. Relative error is sort of small. However, it's not really great if you want to do a specific scientific investigation that's limited to a certain local area. So our navigation capability has got a whole lot better. We are now at the point where if you pick a spot at the top of the Martian atmosphere, we can guarantee that we'll deliver your spacecraft within 2 kilometers of that spot. And that's pretty good. Now, the thing that it gets interesting is that's at the top of the Martian atmosphere. There's a whole lot of dispersion that happens between the top and the bottom of the atmosphere because of atmospheric winds and stuff like that we don't completely understand yet. And the end result is at the surface, what that means is we'll put you somewhere inside an ellipse that's about 10 by 20 kilometers. Again, that's not too bad at the end of a 300 million kilometer traverse. But anyway, we got down to the surface, and a couple of things were sort of fun to take a look at. There were scour marks right here on the surface where the jets of that rocket-propelled helicopter actually impinged on the surface and kicked a whole bunch of stuff up. There was something that was completely unexpected. We looked at the surface of the rover itself, and it was all covered with crap. Basically a whole lot of dust and rocks that got kicked up by those jets and actually got tossed on top of the rover itself. We actually hadn't thought about that problem. And so that one was a new one for us. A later mission, which I'll talk about in a while, that will fly in 2020, just to prevent this exact problem, we've taken those jets and tilted them out 1.5 degrees additional, and we won't get that stuff impinging back on top of us. Took a first set of color images of the surface of Mars near the landing site to take a look around at what was going on. Again, you can see these sort of discolored spots here that are a little bit grayer or almost gray-blue. Those are the scour marks that we just saw. And off in the distance, here's Mount Sharp, that 5-kilometer tall mountain that's in the center of this 90-kilometer diameter crater that actually is the area of interest. That's where we want to go. If you look around where we are at the landing site, this whole region here looks actually sort of pretty flat and featureless. It's basically a big, rocky, sandy, dusty golf course, which is exactly where we wanted to land. It's a nice, safe landing spot. Unfortunately, it's relatively scientifically boring. All the geologists took one look at this and said, I want to look at one rock, then I want to get out of here and get to the fun stuff. All the roboticists and the engineers are kind of going, but wait, we just put you on another planet. Let's enjoy this for a while. And the scientist said, yeah, you put us on another planet in the really boring part. Let's get out of here. And so we started to drive. Now, the first thing that we did, and this image is really dark, but let's take a look and see what we can do. One of the things we started to do is the wheels, the 6 wheels that are on board the rover, are basically made of solid pieces of aluminum. We take a really, really big block of aluminum, about this big, a cube of aluminum about this big. We stick it on a 5-axis CNC machine. We walk away for about 48 hours. We come back, and here's this wonderful rover wheel and a pile of chips about this tall. And then we do that 6 times over, and we stick them on the bottom of the rover, and we start driving around. We went through an enormous amount of analysis associated with the design of these wheels, and one of the things that we found was different about the Martian environment than the way we designed the wheels was that there were a whole bunch of rocks in the landing region that were a lot sharper than we expected. And as a result, the skin of the wheels in between these chevrons, which we call the grousers, are basically tread of the wheel, was thin enough that these sharp rocks could actually puncture through. And over time, as we started driving around a lot of sharp rocks, we started to get a lot of wheel wear associated with the wheels. Here is, after 150 sols, basically 150 Martian days, basically 10 times that distance, you can see the big gaping open holes. Okay, so that's the sort of wheel wear that we've been experiencing as we've been driving during the course of the mission. Having noted that, we've also done an enormous amount of testing and analysis to indicate this is less than 30% of the life of the wheel. We've got at least 3 times this distance that we're capable of driving before the wheels really start to fail. We've actually been able to figure out certain ways where as bits and pieces of this thing break that we can get rid of them and still keep driving with no problem at all. So they look pretty bad, but they actually function pretty well. The one other thing I'll notice, and we all got really, really worried, we started to see all these holes that were being punched in the wheels. Okay, story time. Is we actually also designed a bunch of holes in the wheels. If you look here and here, those are not rock punctures. Those are actually holes that are supposed to be there. And the question we immediately get is, why in the world would you design a wheel with holes in it already before you even get to Mars? Well, it's actually really simple. One of the things that we wanted to do was have the ability to take the cameras on the rover as we would drive across the Martian surface, have the cameras look back at the wheel tracks we left behind us. And we wanted a fiducial mark on the wheel so that with each revolution of the wheel, it would leave a print indicating this is basically one circumference distance that you've been able to drive. And so visually, we could calculate our odometry. If all the sensors on the machine failed, we could just by looking at the tracks and counting the number of fiducial marks, we could figure out how far we've been driving. And so it was a really nice way to check our progress. Okay, so that's the desire. It makes a whole lot of sense, no problem at all. Well, what do you want your fiducial mark to be? We actually had to design it in there. And let's see, how to tell this story. We had one particular engineer who said, I'll take care of it. He was working on the wheel design, and he'd been doing a really good job. So he was like, okay, fine, go ahead and take care of it, no problem. Let us know what you come up with. And we just never really thought about it at all until about 6 months before launch. Somebody happened to be reading a German ham radio magazine. And there's a little sidebar story in the German ham radio magazine about the Morse code encoded on the Mars rover. And we all sat up and said, what are you talking about? Okay, let's divert for just a moment. The prior rover missions, Sojourner in 1997, Spirit and Opportunity in 2004, when they landed. If you look at the photographs coming back from the surface of Mars associated with those rover missions, one of the things you cannot help but see is the Jet Propulsion logo, Jet Propulsion Lab logo everywhere in every single photograph all over the place. NASA basically said to the engineers at JPL, look, we understand you're proud of the place where you work. We understand institutional advertising and marking basically what you guys have built. However, you're overdoing it. This is getting a little bit ridiculous. Having 5 JPL logos sitting on the top of a rover is overkill. So we actually wrote into the formal project plan for the Curiosity rover, there shall be one and only one Jet Propulsion Lab logo on the rover. There shall be one and only one NASA logo on the rover. It'll be visible from this camera position. It'll be on the top of the deck of the rover, and that's it. And the guys at the Jet Propulsion Lab said, fine, we'll live with that, no big deal. Now back to the surface of Mars. And one engineer late at night saying, I have to come up with a fiducial mark for the wheels that has to be able to be discerned. What in the world would I possibly put on the surface of my wheel? And yes, you guessed it, those holes, if you look at them, there are big ones and there are small ones. They convert to dots and dashes in reverse so that as you look at the imprint left on the surface of Mars as the rover drives, every 1.7 meters, there is in Morse code JPL. So, now we found out about this, like I said, about 6 months before launch, by which time we're deep into a process called ATLO. The entire spacecraft is being buttoned up. There is nothing we can do about it at this point. We called in that engineer and talked to him and basically said, that is so freaking clever that we're not going to fire you, but don't do it again. And as a result, there's only one JPL logo on the rover, but there are tens of thousands of JPL imprints on the Martian surface itself as you look at the rover tracks. Who said engineers weren't sneaky? The scientists, meanwhile, have said, okay, fine, you guys have been having lots of fun with your Morse code and all that sort of stuff, but what about our results? We've been driving off this entire time about a half a kilometer east towards something called what later became known as Yellowknife Bay, which was this convergence of 3 different types of geology at one point, where the scientists were incredibly interested because if we can get to that one point, in one place we can sort of study 3 different types of geologic units. They became known as the cratered unit, the hummocky unit, and the fractured unit. If there are any geologists in the room, I will let you explain all this. I used to be able to, I could do it one time, and I got it right, and I'm just going to rest on my laurels with that point. And not try to do it again. But the whole point was the geology team basically said, if we can get to that one place, study these 3 different types of geology from one location, we'll be able to tell a lot about the formation of the crater itself and the history post-formation that the crater went through. And so they were very interested in getting there. So we actually spent about, we planned to spend about 4 months driving very slowly, this half kilometer over to this region so we could do investigation. But as we're driving, again, remembering one of the things we're trying to understand about the surface of Mars in this location is the water history of this place. We're sort of driving along, and we basically commanded the camera as we're driving to sort of look down at the traverse path as we're executing it. And all of a sudden, the geologists start screaming and yelling and jumping up and down and saying, stop! And the engineers are kind of going, but you told us to go. And what they realized was at that particular moment, purely by happenstance, we happened to look down at the right time, but we were driving through the remnants of an ancient stream bed right at that moment with the rover. That basically they were able to look at the conglomerate rocks that were sitting there that we were driving across, and they understood, based on the shape of the rocks and the way that they were all cemented together, that this was an ancient stream bed, and we actually stopped to actually do pH measurements of the rocks and the cementation between the different pebbles, and could surmise from that that this was a place that for a period of hundreds of thousands of years, approximately 1.4 billion years ago, there was a stream running through this region that was about 2 meters deep, moving at 1 to 2 meters per second, again, for tens of thousands or even hundreds of thousands of years, that caused this place to be created. And we found out by looking at the pH of the cementation between the pebbles that this was very neutral water. It was very slightly acidic. Basically, if you or I had been there on the surface and taken a drink of this water, we would have thought it was absolutely fine, a little bit cold, but it was absolutely fine to drink and consume. And so all of a sudden, by accident, while we're on our way over to the place that's supposed to be scientifically interesting, basically 3 months in, by accident, we found one of the major scientific objectives of the entire mission, 3 months into the entire process. One of the other features that we also spotted, again, for the geologists in the room, you guys know why this is important. We saw a feature called crossbedding, where basically, again, this is something that happens on Earth where you've got lots of flowing water over long periods of time that laid down sediments in successive layers that sort of slip back and forth across each other. And that's exactly what you've got here, where you've got intersecting planes of sedimentation that have been put down over millennia, and then later on this rock was then re-exposed by erosion, and again was another very, very strong indicator to understand the water history of this particular region on the surface of Mars. Okay, ChemCam, the laser. We have a robot with a laser on its head. We want to use it just because I have a laser, and you got to do something with it. And so this is one of the test shots of actually what happens. Basically, you can, up to 100 meters away, you can fire the laser, and it'll fire in pulses, very, very short, brief pulses, that will actually vaporize the surface of whatever it hits. In this case, we did 5 successive pulses against this rock to take a look at, and then basically there's a spark that's created, and the spectrometer looks at the spark, and basically from that can discern what the composition of the rock or whatever material it is that you're shooting might be at a reasonable distance. Okay, what does that process actually look like? I want to be really, really clear. It's not that. Yet. This is what you actually get. This is Coronation, which is the very first rock that we shot from a distance of just a couple meters away, and across the top of the image, that is the actual resulting spectra that was acquired by the ChemCam instrument. And a couple of features that pop up here, the titanium and manganese spikes that were showing up in the mid-wavelengths. If you look out here in particular, one of the things that was really interesting is this was 5 pulses all in the same spot, and in almost every case, the resulting spectra perfectly overlaid in the case of all 5 shots, except the interesting one was in this case, the hydrogen spike on the first shot was uniquely different, and then the following 4 all laid right on top of each other. So basically there was some sort of surface material that was different that the first shot burned through, and then each successive shot said, oh, the stuff beyond that point is all the same. What this all translated into, when you look at all the really cool pointy squiggly lines, a geologist will turn around and say, this is basalt, which is exactly what it was, which is one of the expected materials that we found on the surface. So in a very, very close region, you have both sedimentary and volcanic rocks in the same environment. The other thing we also have the capability of doing is we have this camera that's out at the end of the arm. The camera primarily is used to basically take close-up microscopic images of the rocks and the soils and the things that are of interest that the rover can drive up to. But being a vain little witch, our robot also has the capability of doing interplanetary selfies. So yes, we can take the arm, stick it out like this, turn it back, and take a picture of the rover itself. The only thing that's really different is because of the width of field of the view of the camera, it actually can't just take one picture like this and grin. It actually has to mosaic together. I think this one is 42 different images that are all sort of tiled together to create that one selfie. And it's because as it does that, it has to sort of slightly move the camera around from image to image. As a result, you don't actually see the robot arm that's holding the camera because it moves from frame to frame, and then when the frames are all stitched together, the arm just sort of disappears in the process. But it is there. So yes, this is the robot taking a picture of itself. There's not someone else on Mars taking the picture of the rover. We do get that question. I mentioned that there's a weather station on the surface of Mars. excuse me, the REMS instrument, which is built by the Italians and contributed to the process. 2 little booms that stick out the side of the mast that holds the camera that basically can take weather information. They were designed to do things like take temperature, take pressure readings, take wind speed and wind direction. Remember that picture I showed you just post-landing where all these rocks have been kicked up and thrown on top of the rover? The rover survived that process with no issue at all other than the fact that it was now really, really dirty, except one rock happened to perfectly home in on this REMS boom and took it out. So one of the 2 booms did not function, and as a result, we don't know wind direction. We can tell you wind speed, temperature, pressure, all that stuff with just the one remaining sensor, but we can't tell you which way the wind is coming from. For the Mars climate scientists, that actually is really important because they're trying to identify predominant wind directions. But I grabbed this one 3 days ago. So as of 3 days ago, the air temperature on the surface of Mars at Gale Crater had a maximum temperature of negative 28 degrees C, a minimum temperature of negative 79. The ground temperature was negative 6 to negative 83 with an atmospheric pressure of 815 pascals. Sunrise was at 5:51 a.m., sunset at 17:34 p.m., atmospheric opacity was sunny, ultraviolet radiation was near fatal. Please don't go outside without your sunglasses. We get these weather reports every single day. Every single day it says, it's sunny on Mars. The pressure reading, this one's just very, very quickly, it's kind of interesting because what you actually have is a Martian atmosphere that gets heated up by the sun enough that basically just before dawn every day, the atmosphere that's being heated up by the sun as the sun rises basically forms a pressure wave. And this pressure wave gets pushed just ahead of the sunrise terminator in a big wave that basically goes all the way around the planet as the planet rotates. And there's basically, like with every wave, there's a peak and a trough. Around midday, there's a low-pressure trough that's following that process all the way around the planet. So basically, there's this huge atmospheric wave in almost perpetual motion circling the planet as the planet rotates every single day. So if you could do atmospheric surfing, you would be in heaven. The amplitude, the magnitude changes during the course of the different seasons, but the existence of the wave is pretty much a constant. We do have an ability to actually scoop up soil from the surface and ingest it into the SAM instrument that I mentioned. The other thing we're also doing is taking a look at the surface radiation and trying to understand how it will affect people. The distilled down version of this entire image is that the radiation that a human being, assuming no effort to shield them, a human being would absorb what are called 1,000 millisieverts of radiation during the course of a cruise to Mars and a 500 sol stay down the surface and a cruise back home. All right, what does that mean? Well, like I said, 1,000 millisieverts, or 1 full sievert. The lifetime occupational dose limit in the United States for a nuclear power plant worker is 50 millisieverts. So it's basically 20 times your lifetime occupational dose that you would absorb in the course of this trip. So one thing that tells us is we have to have some fairly serious radiation mitigation efforts associated with the first human trip to Mars. Now that we know how bad the problem is, we know how to engineer some solutions. But it is a fairly serious problem that we have to mitigate. I also mentioned that we have a drill on board the rover. It's stuck out at the end of this arm, and basically we're allowed we use it to come down in contact with the rocks and actually drill holes into the interior of the planet. This is the first time that this has ever been done. It was a real surprise the first time that we did it, because normally when you look around the surface of Mars, it's really, really reddish. It is, in fact, really, really rich, iron-rich soil and sand that covers the entire planet, that gives it the particular color cast that it has, because actually, in effect, the surface of the entire planet is rusting. It actually looks an awful lot like what you're going to see in the outback in the middle of the Simpson Desert. It's a very similar color that covers everything. And so we thought the entire planet was going to be like that. To our surprise, the first time we drilled a hole through the surface of a rock and into the rock interior, about 2 centimeters down, and started looking at the dust that was popping up, it was all gray. It was a distinctly different color, which we never expected. We thought this rust coating, this iron oxide coating, was pervasive all the way through everything. It turns out it's not at all. And in fact, there's a whole different set of chemistry going on associated with the interior of rocks that we don't understand yet. This one, I'm hoping you can see it. People have asked occasionally, basically the same sort of people who are convinced that we never actually landed on the moon. And by the way, yes, we did. We occasionally get those folks that come to say, how do we know you're not faking this whole thing? It's not all done on a Hollywood sound studio. Well, that's because we have orbiters at Mars who are constantly circling the planet several hundred kilometers up. And we used one of them, the Mars Reconnaissance Orbiter, which has a very high-resolution camera, to overfly the region where the rover was traversing and actually look down. And if you look really, really carefully, see these two little blue dots right there? Those are the scour marks from where the rover landed. And this large area is all the material that was blown up by the rocket-propelled helicopter as it came in and landed. And if you look really carefully, you can see two little parallel lines that follow this path. And those are actually the wheel tracks of the rover as it drove over here to this Yellowknife Bay region. And that bright reflective dot right there is the rover observed from orbit 220 kilometers up. So we have photographs that prove we're there. And if you, unfortunately, this image doesn't have quite high enough resolution, but these two parallel wheel tracks, if you were to zoom in on those really, really, really closely, you would see JPL, 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 JPL. So where have we actually driven since then? Okay, so this last image. This is sort of the thing I showed you that was our plan of where we wanted to go, this half kilometer from the landing site over here to Yellowknife Bay, spend several months studying this. The geologists got all really excited. They all jumped up and down the hall. The scientists associated with ChemCam were really, really excited. The first time we actually used ChemCam, they ran up and down the hall going pew, 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 because we got to use the laser. The engineers were really, really excited because we were driving over all sorts of really cool stuff. So everyone was really, really happy as we went this half kilometer over 6 months. The only problem was the place that was scientifically really interesting was way, way, way down here. That half kilometer that took us 6 months to do, see this little sort of left to right bit up here at the top? That was that. Okay. We have spent the 4.5 years since then doing the rest of this yellow line, and we're currently, as of today, right about there. We're on Sol 1,890 of the mission on the surface of Mars. And we have given various different names to the different regions as we've driven through them. I'm just going to hit a couple of them really fast to sort of show you what some of the different environment is like. A couple of these, I think maybe it's a little bit some favorites. This is a region where we actually encountered a sand dune. The dune is about 1.5 meters tall. It's made of very, very fine-grained material. It's almost the consistency of like talcum powder, so really, really soft, fluffy stuff. And we were actually very concerned about whether the rover would get bogged down like a big sand trap and whether it would be dangerous to drive across that or not. So this region actually became known as Dingo Gap. And we spent 3 weeks studying this region, trying to figure out is it going to be safe for the rover to drive across this little sand dune, the 1.5 meter tall sand dune or not. And then it actually took us 1 day just to drive over it. We then got to a region called Garden City. And this one, again, for the geologists in the room, this one's really sort of interesting and a lot of fun because there's all sorts of different stuff that's going on here. Where you see Mount Sharp, this 5 kilometer tall mountain in the background, but basically down here lower in the near foreground, you've got all this exposed volcanic material that's been pushed up, but also over the eons has been heavily fractured. There's been inflow of waterborne materials that then has accumulated in the cracks, re-cemented. The outer material then got eroded away and left these sort of veins that were previously crevasses and cracks that have been backfilled with then harder materials that were then freestanding. And so if you actually take a look closer at this, this is the sort of stuff that you see. This stuff is a couple of centimeters tall, 3-4 centimeters tall in some cases, but there's this whole region just full of this stuff where the harder, persistent material is this whiter, lighter stuff, this sort of freestanding veins and fins, and the softer original material has all been eroded away and has slipped out. We found also a lot of perchlorates in this region, which again was telling an awful lot about the history of the geology in the region. Further along, we got to the beginning of a region called Murray Buttes. This was just one particular set of rocks that were exposed. And again, here, if you look closely, you see all sorts of stratification going on back and forth here. So we could drive up into this region as close as the rover was able to navigate and get a look at this stuff close up and see what it was actually made of and look at the chemistry of it as well, as you sort of start peeling back the pages of the history book that was being revealed by this crater. Another region of Murray Buttes with even more dramatic stratification going on, as well as some really interesting stuff that's been exposed, and a little rock that sort of looks like a face if you look at it sideways and squint. Again, that does not mean life on Mars. Beat me to it. And one final one to show you just sort of the things that are going on during the traverse. This is from about 2 months ago. And this one's really sort of interesting because we're now well up into the foothills of Mount Sharp. And one of the things you notice here is look at the variety in color in that frame of the different elements of the environment, with this very, very distinct sort of purplish cast on all the stuff down at the bottom, and it gets redder and darker and a little bit more pastel as you sort of progress up higher in altitude and further back in distance. The purple material down at the bottom is very, very rich in hematite. Again, another indication of the past history, the water history of the planet. Hematite is a mineral that when we find it on Earth, in almost every case, it is formed with very, very water-rich regions. Long-term standing water is sort of a hallmark of hematite. Where we find it on Mars, we believe it is an indicator of long-term standing ponded water. And to find an entire region that's basically just covered with this stuff leads us to believe that at various different points during the history of this crater, this wonderful big 90-kilometer around crater, it actually was a lake at various different times. And then the water receded, came back, receded, came back again. Okay, a couple of things real fast just to mention a few of the technologies that allowed us to do this investigation. Pico TPS, a thermal protection system that allowed us to basically translate from 20,000 kilometers per hour down to 0 at the surface. It was a whole new invention. A whole bunch of instrumentation on the heat shield to actually tell us how hot the thing got. The precision landing I mentioned before, we're now able to actually relatively precisely put something on the surface of Mars instead of somewhere inside a 300-kilometer circle. Advanced supersonic parachute, the largest one ever built. The descent range, descent engines, descent radar, and the sky crane were all things that I've mentioned earlier. The nuclear power source that we use to actually power the rover. We have 10.6 pounds of plutonium dioxide inside this cylindrical structure right here that's sitting cooking at about 600 degrees C, 420 thermocouples wrapped around it that generate about 100 watts continuous. So basically, with the power of a small light bulb in your house, we are powering this entire rover. That provides the energy to move it, to do all the computation, to do all the science operations, to do the communications, and everything else that this rover does all comes from that very, very small power source. There are onboard batteries, so we basically can store up and charge the batteries on an ongoing, continuous trickle charge basis, but effectively it's all coming from that little thermal source right there. And autonomous rover navigation. As a roboticist, this picture to me is one of the most amazing pictures anywhere. Everyone else looks at it and goes, wow, Arizona. But what this picture shows is the path that the rover chose to take to navigate from point A to point B. The way we command the rover. So again, you have a planet that, depending on where Earth and Mars are in their orbits relative to each other, at the speed of light, it takes a signal anywhere from 22 to 45 minutes to make a round trip between Earth and Mars. So what that means is I can't sit there and in real-time joystick this rover as I try to drive it. What I've got to do is basically tell the rover, here's where I want you to go, and the rover has to be smart enough to figure out how to make that happen. What we do is we actually literally look at a computer display of the images that came down yesterday and designate a target and tell the rover, go there. The rover is smart enough to do one of two things. It'll attempt to execute that, and it's going to send back one of two signals at the end of the day. Either, I got there, what do you want me to do next? Or, I ran into trouble, I need help. And those are the only two acceptable responses. If there's no response, then, okay, that's an entirely different deal. But what happens when that occurs? Like I said, we designate a target. The rover has to be smart enough to understand the terrain in front of it, use its cameras to figure out that rock that's in front of me, is it big enough that it's a hazard, and do I have to drive around it, or can I just drive over it? If I have to drive around it, as I start to do that, I'm deviating from the path that I want to follow. When do I know I'm past the hazard, and how do I get back to my desired path to actually get to the goal that had been set for me? So it's figuring all that stuff out all by itself 300 million kilometers away. If things go wrong, and if this doesn't work, there's no one within 300 million kilometers to reset the blue screen of death. So the fact that this worked, and what you're seeing off in the distance is a path that basically had the rover come in, identify a hazard, drive in a circular arc as it changed direction, then execute that directional change all by itself to avoid a hazard very successfully, completely autonomously, 300 million kilometers away. For a roboticist, that's a really big freaking deal. So we like that one. Effective outreach. There was a lot of press coverage at the time of landing. There's been a lot of press coverage ever since then. That's been amazing, fun, cool stuff. I'm not going to go through all the different things that were there. We got press coverage out the wazoo. I mean, we hit like the top above the fold front page on 392 of the 393 major newspapers on the planet. The one that we didn't hit, there was a picture of a girl in a bikini on an Italian newspaper. I'm not making that up. The other thing that we do is we make all the data, and in particular the images that we get from the rover, available as fast as we get them, because we want the people of the world to come along and explore Mars with us in real time. Okay, what do I actually mean by that? For example, the images that we get downloaded from the rover twice a day, as fast as they are received, we put them up on our public website in full resolution. You can log on to mars.jpl.nasa.gov/MSL, and you can see the images that got downloaded this morning as fast as the science team sees them. So by the way, as a side statement, which means we can't hide anything, because you guys are getting access to it as fast as we are, in some cases faster. We've had cases where family members of the science team who are on the west coast of the US, their family is on the east coast of the US. The family wakes up in the morning, they check the data site, they see what's going on, then they'll call the science team member of their family who's out on the west coast 3 hours behind them, and they basically leave a voicemail message that says, when you get up, this is what you need to look at. Now, when, for example, your spouse is one of your scientific collaborators, that's okay. When it's your 7-year-old little brother, it sort of pisses you off. But one of the other things that happens is the people beyond the science team who have access to this stuff start to do really, really cool things with it. Okay, so for example, let me mention, I'm sorry, before I get too far, well, let me talk about Midnight Planets for a second. Midnight Planets is an application. It runs on an iPhone, on Androids, it runs on a website, everything else. If you go to their website, you can grab it, or you can run it just in a web browser itself. Basically, it was written by a guy in Washington State in the US who is not affiliated with the science project at all. He's just an interested member of the public who thought the stuff was cool. He grabs those images every single day as they're downloaded from the spacecraft. He knows how to decode the tags, the metadata tags that we have on the images to understand when the image was taken, which way the camera was pointed, which images were done before and after other ones, the filters were used, all that sort of stuff. And he stitches them all together. He's written an application that automatically stitches them all together, creates a 3D representation, a wraparound cylindrical representation of the surface of Mars based on that day's imagery, that he then basically throws out to the public and says, here, have a look at the surface of Mars by, on your phone, take a look and see what the surface of Mars is like. His stuff is so good that the operations team now uses it. It's like, this is really cool. We hadn't done anything like this. And you can go to midnightplanets.com and get your own copy, and every single day you get updated on what the surface of Mars looks like based on what the rover saw today. Because you haven't presumably done that quite yet, because I just told you about it, the set of images that are running across the top, they're images that I grabbed this afternoon about 3:30. is stitched together in a really, really quick panorama for you. These images have been on Earth all of maybe 6 hours. You're the first audience to see them. And this is a good representative sample of the sort of stuff that comes down constantly. And really quickly, what you're seeing here is basically the rover that is Mount Sharp in this view is sort of like in where I am. The back of the rover is right here, and here's the thermoelectric nuclear power unit. Here's one of the wheels, the second wheel. It's sort of warped right now in the panorama, but you sort of get the idea. And of course, you can see the rover tracks leading back in the direction from which we've come that we've left behind. And oh, by the way, there's a little fiducial mark, and there's one, and there's one. Okay, so, and then off in the distance here, you might think that this is Mount Sharp, but actually, as I said, Mount Sharp is sort of where I am in the frame of reference of this image. What you're actually seeing over here, this ridge line of mountains off in the distance is actually the rim of that crater about 40 kilometers away, viewed from the inside of the crater. So that actually wraps all the way around us for where we are, and you're actually seeing it from 40 kilometers away. Okay, so that's a quick discussion of sort of what we're doing on the surface of Mars right now. And yeah, I knew it. I apologize. I went over. But I'm almost done. What happens next? I showed you that sort of that schematic back in the beginning of sort of what we think we want to do, or what we have done the past decade, and what we think we want to do out in the future. The next rover that we're going to fly in 2020 is the twin sister of the Curiosity rover. It is effectively a build-to-print copy of the rover with a different science package on board. So from the roboticist viewpoint, mine, because I'm the one who's important, the rover, the important parts of the rover are virtually identical to all the really cool stuff on the Curiosity rover. Oh, and there's some other science stuff. The science package that's on board, all the really cool stuff like the drill, the camera set, the laser on the top of the rover, all that stuff, we're not replicating. Instead, we're doing an entirely different science package that is specifically tuned towards looking for biosignatures and exobiology signatures and life signs on the surface of Mars. It's the first ever what we call astrobiology mission for that dedicated purpose of actually looking for signs of past life on the surface of Mars. So there's going to be an entirely different science package that's already been prepared or is in preparation right now. They'll be plugged on the rover. The rover will be launched in 2020, get there in early 2021, and then begin operations. At the same time that the US is building their rover, the European Space Agency is also building another rover of their own with a different science package on board with the same ultimate purpose, looking for biosignatures on the surface of Mars. Now that we've shown that there used to be a lot of water, we've proven it, and we've shown through the Curiosity rover that the environment that was there that was capable of supporting life, if it ever actually happened to have existed. Now the next step in that hunt is to basically say the environment was there, the chemistry was there, the water was there. Let's find out if life ever really started on another planet and see if we can actually identify it and find it. And so that's what we'll be doing in 2020 and for several years after. And then eventually, and I cannot tell you when it's going to happen, but eventually, some number of years after that, there'll be another rover or rover mission that is going to do something like that. All the stuff we're doing, remember the 4 strategies I mentioned back in the beginning, and we're sort of evolving towards being able to have the resources to support a human mission to Mars. Eventually that is going to happen. I can't tell you exactly what year it's going to happen right now, but I can tell you with as much certainty as I know how to have. The first human being to set foot on the surface of Mars has already been born. I don't know who he or she is. I don't know what country they're from. I don't know exactly how old they are. But I believe that person already exists. And within our collective lifetimes, the first humans are going to set foot on another planet, not just on a moon of our own planet, but on another planet for the first time. One of my own personal goals is I want to stick around long enough to see it happen. But there's a whole lot of work that's going to happen between now and then to prepare the way for that first human mission to Mars. A whole lot of preparation done by robotic missions to understand the planet better, to understand the resources that are there that the human mission will make use of. A whole bunch of site preparation. Think robotic assembly of habitats that has to be done before the people ever get there. The architecture basically is predicated on the idea that we will send a human mission to Mars when their home on Mars is ready. So we actually will build that before they ever get there. And not only will we build their habitat on the surface of Mars before they ever get there, we'll also provide their return ride and everything they need to get back before they ever get there. So they have the ability to return safely. A lot of people ask, knowing what you know about the planet and spacecraft and everything else, would you ever go and fly to Mars? And the answer is really quite simple. As long as you tell me I can come back. Yeah, I'll go. Anyway, so that is way too long. I apologize for running over, but I warned you it was going to happen. I can go on for about another 3.5 hours and just begin to scratch the material that I've got. But that's a real quick flavor of sort of what we're doing with Mars exploration, how we're accomplishing some of it with rovers like the Curiosity rover that's up there and operating right now. And I'm available for questions if anybody has any. I appreciate your attention. Thank you very much.